All right, so here we kind of talk about the practical implementation or realization of something like a unit step function or a unit impulse delta function. If you remember during filter design in module 2, we kind of talked about how ideally we would want something like a low pass filter to have a response that looks like this, right? Where it basically passes all these frequencies perfectly, and then at some value of frequency, it just completely stops passing frequencies, and that response is zero above that frequency, right? That's kind of what we looked at for an ideal low pass filter. But then we noted that this isn't practical. If we want to implement a filter in real life, it's probably going to look a little bit more like this, where it has some kind of a roll-off, maybe 20 dB per decade, maybe more if we use an active filter or some kind of cascaded filter. But we couldn't achieve a perfectly sharp cutoff response. We could achieve something close, and that was good enough for a lot of cases. Well, the same goes for these types of functions, like a unit step function. So, like I said, in circuits, the application of a unit step function might be something like a pulse source, where we want our voltage to go from some value to some other value. Usually it will be 0 to some final voltage. And we ideally want that to happen instantaneously. And that's what happens with the unit step function. It basically goes from 0 to 1 in an instant. It's an instantaneous change in the level of that signal. Well, that's all good and well, and that's the ideal step function here. Imagine we take that voltage or that U of t and scale it by some value VO. I guess we can call it VO in this case. That's what they're calling it, or V0. Then we get a unit step function that's scaled by VO, which means that this signal would be equal to basically 0 for t less than 0, but it would be equal to VO for t greater than or equal to 0. So a real unit step function, or a step function, or a pulse that we would provide to a circuit, it's not going to have an instantaneous rise time. It's going to have some delta t, right? Some difference in time where it's ramping up from 0 to its final value. Whether that's a nanosecond or a picosecond, it's not going to be 0, because in real life, things take time. We cannot transition instantaneously from one voltage to another. That's just not realistic. So a realistic step function has some kind of slope here. And so that's important to note. We may or may not take that into account when we do analysis of circuits, but it is important to note practically that that is the case. And the same goes for the delta function. Of course, if we want to implement a very, very narrow, very, very large pulse, we cannot get a height of an infinite height. That's not practical. And we also can't get an infinitesimal width. That's also not practical. So what we can look at is something like what I have down here, this rectangle model. This is from the textbook. Rectangular model, or the rectangle model, and it's basically saying I can take this spike, which I am telling you has a height of infinity and a width of basically 0, and I can look at it as a rectangle, basically a rectangle that has some width. This width is 2 times epsilon, and the height is 1 over 2 times epsilon. And so of course, if we take any rectangle, we know that its length times its width gives us its area. And so in this case, the length of this rectangle is 2 epsilon, and the height is 1 over 2 epsilon, right? And so if we take the area, that would be 2 epsilon times 1 over 2 epsilon, which gives me 1. And so what it's basically saying here is if we shrink epsilon, right, if we make epsilon smaller, this thing gets narrower, but it also gets taller, because this epsilon in the denominator makes the height get bigger. And so if I get a smaller epsilon, I get a bigger height. If I get an even smaller epsilon, I get an even bigger height. And as I squish this epsilon to 0, my height goes to infinity. And at the point where epsilon is 0, that is where the delta function is defined. It's defined as the limit of this rectangle as epsilon goes to 0. Because if we let epsilon go to 0, right, the width of this thing goes to 0. And if we let epsilon go to 0, the height of this thing goes to infinity. And so that is the definition of the delta function. The definition of the delta function is we basically take this rectangle with 2 epsilon width and 1 over 2 epsilon height. And if we take the limit of that rectangle as epsilon goes to 0, we get a unit impulse, which has no width and infinite height. Okay? Just important to note practically, I think the next slide kind of expands upon why this is important and kind of gets into how these two functions relate to one another. And so I'll end this video here and we'll keep talking about this in the next video.